All right. Graphing piecewise defined functions, section 8.1. We're going to come down here to task 2. We're now going to look at what the rule or equation looks like for a piecewise defined function. We didn't write an equation for task 1, and we were just looking at the graph and getting information off of that graph. So now we're going to look at the rule. So first we have to consider a relation in which one value in the domain is associated with two different values of the range. So like in this case, an input of 0 goes to 3 and it goes to 8. It asks, is this relation a function? If you remember from the first video, we talked again about a function having every input has only one output. If we notice here, this input of 0 has two outputs. So it's not a function. Okay. Input of 0 has two outputs. So it's not a function, okay, which is a huge part of a piecewise defined function because, as we talked about, a piecewise defined function up here is a function that has different rules for different intervals of its domain. Those intervals of that domain, those intervals have to be what we call distinct. Distinct meaning different, not overlapping. There can't be anything that's in both of them. Okay, so when we look at the rule for a piecewise defined function, here's what a piecewise defined function looks like if we're looking at the equation. It has different rules. This one has 3 different rules. Each one of these are the rules. They tell you what to do. Like the first rule, I multiply by a -2. I take my input, take my input, multiply by a -2. My next rule is take the input, multiply by 3, and then add the 1. And my last rule is take my input and subtract 1. So those are my 3 different rules for this function, but I use each rule depending on what my input is. Here, if x is, again, this is less than, if I'm putting in an x less than -3, I use, if I'm putting in an x that's less than -3, I use this rule. If I'm putting in x for this next one, that's between, here this x is in between -3 and 2. So here, if it's between -3 and 2, I use the next rule. And here, if it's greater than 2, I use the last rule. But notice the equal to. This has got an equal to, and this has got an equal to. This rule, this first rule, is only used if I'm less than -3. If I actually equal -3, I use this rule. And this one I only use up until the point 2. Once I get to 2, then I use this rule. So there is no overlapping. This one couldn't have an equal on it because then what would I do when I input a -3? Which rule would I use? We wouldn't know. Okay, so it's very important that they're very distinct intervals. So if we want to, we're going to, it's a function. Explain why this relation is a function. Every input has only one output. Okay, that's why it's a function. Every input has only one output because these domains don't overlap. These don't overlap. And they can't for it to be a function. So these first bits here are the rules. These here tell you when to use that rule. Like for what domain values do we use which rule? So now I'm going to graph this. Okay, so I'm going to come in and I'm going to draw in my axes. Okay, so now I need to look at my breakout points. Basically, I need to look at this and decide. So basically, I'm using this rule for everything less than -3. So I'm going to come in with a highlighter and I'm going to find -3. 1, 2, -3 right here. And I'm just going to draw a vertical line here at -3. So I know for less than -3, so less than -3 would be this side of -3. So over here, I'm going to use the rule -2x. Okay. So I write that above there. I'm using that rule negative 2x. So if you remember how to graph that, we would look y equals mx plus b, y equals negative 2x plus 0. So that's going to have a y-intercept of 0. So here, let's switch colors. Let's make this guy red. So let's do him in red. Y equals negative 2x plus 0, y-intercept of 0. So it's got a y-intercept from 0. So I'm going to come over here and use this to graph it, but I'm only going to start it from that green on. Okay, so I'll show you what I mean by that. Y-intercept of 0, a slope of negative 2. So I'm going to go down 2 over 1, down 2 over 1. But that's on the wrong side. That's way over here. I want to graph it over here. So instead, I'm going to go up 2, back 1, up 2, back 1, 2. So starting there. Okay, grab my ruler. Okay, we're going to put it on there. But again, we're only graphing this on this side. There's my arrow. There's my negative 2x. Now, of course, this does not include, this is a strictly less than. So I need an open dot here. Because when I actually equal 3, when I equal negative 3, I use this equation. So in between negative 3 and 2. So I'm going to come in and I'm going to grab my highlighter again, and I'm going to mark this at 2. So now on this in between in here, I'm going to use this middle equation, this 3x plus 1. So y-intercept of 1, so I come and mark it, y-intercept of 1, slope of 3, rise of 1, 2, 3, over 1, 1, 2, 3, over 1. Okay, so I connect those dots. Again, grab my ruler. Oh, my ruler went away. And connect those dots. So now I'm going to do that in between those two. So really, graphing piecewise defined functions is just graphing each function. Okay, just until that highlighted. But now for this highlighted, again, this highlighted is an equals. So I'm going to have a solid dot here. Because again, these both can't be solid, or else it wouldn't be a function. It wouldn't pass, remember that vertical line test? Or basically an input of negative 3 would have 2 outputs, not a function. But this does not equal at 2. So I need an open dot at 2. So there's my open dot. Make your open dots nice and big. And then now we need to do the very last rule for x is greater than, so I know we'll do purple. So for this guy, for stuff on this end, I'm going to do x minus 1. So y-intercept of negative 1, slope of 1, up 1 over 1, up 1 over 1, up 1 over 1. And I just want to get enough points out here. Bring my ruler in. Connect those purple dots. But again, I'm only doing them from the green over. So from here on up. Okay, and this is going to have the closed dot because it's equal to right there. Okay, so there we've graphed our function. So again, this is a piecewise defined function because it's graphed in 3 pieces, right? We've got this red piece, we've got this green, and we've got this purple, but all 3 pieces together make up this function. Okay, so which part of the graphs are line segments? Line segments have 2 endpoints. To be a line segment, you need 2 endpoints, whereas a ray only has 1 endpoint. Array only has 1 point. So which part of the graphs are line segments? The line segment part would be this green bit. Basically from that negative 3. The negative 3 less than or equal to x less than 2 is a segment. But then the bits less than negative 3, that's array. And the bit greater than or equal to 2, that's array. Because they go on for forever. Hence, notice we put arrows on the end of those. This does not have arrows because it only goes from here to here. And then it ends. Okay, now we're going to evaluate some functions. So here, and this is where you have to be careful on what interval you're in. So here, if I want to evaluate f of, for this first bit, f of negative 3, I have to look up here and decide which one of these does it fit in. It's equal to negative 3, so equal to negative 3 would be this one, so I put it into that equation. So that would be the rule I would use. I would use the 3 times x is 3, oh, negative 3, sorry, plus 1. So 3 times negative 3, negative 9, plus 1 is negative 8. So that tells me that the point negative 3, negative 8 should be on this graph, which it is. That's this point right here, that negative 3, negative 8. Okay. So f of negative 3, again, function notation, f of negative 3 equals negative 8. Now we want to do f of 0. Again, I have to look, what interval are we in? Are we less than negative 3? No. Are we in between negative 3 and 2? Yep, so that's the rule I use. So I would use the 3 times x plus 1. 3 times 0 plus 1 is 1. So f of 0 equals 1. So that tells me an input of 0 gives me an output of 1. And again, I could also get this from the graph. An input of 0 gives me an output of 1. Yep, it's that bit right there. So now that I have the graph, if I want to find f of 2, I could use the graph. F of 2, 1, 2 is a 1 using the graph. But that would also tell me I actually need to use this rule, f of 2. So I could use the rule, it's x minus 1, which again still gives me 1. So whether you use the rule or use the graph, once you have the graph, you can do it either way.